Welcome to specific heat capacity. Recall the example from the last video where holding an ice cube in your hand resulted in heat flowing from your hand into the ice cube. The energy in your hand, particularly kinetic energy, was lowered, so you feel colder. So the temperature of your hand has gone down also. The ice cube, on the other hand, is gaining that heat that came from your hand and is melting, which indicates that its temperature is rising. So clearly, there's a change in temperature that accompanies the transfer of energy. And in this lesson, we're going to look more closely at how much heat is needed to raise the temperature of a substance. Or more generally, what we're going to be asking is how much heat is needed for a temperature change. And the short answer to this question is it depends. So naturally, the next question is, what does it depend on? Depends on what? And to figure out what it depends on, we're going to look at two cases here. In case one, I have a glass of water and a bathtub of water. Both of these samples will boil at 100 degrees Celsius, because all pure water samples boil at 100 degrees Celsius. The question is, which of these will I have to add more heat to bring it to boiling? Most people would immediately choose the bathtub, because intuitively that makes sense that I would need to add more heat to the bathtub full of water to get it to start boiling than I would to a cup of water. So why would someone pick the bathtub as the one that would take more heat to bring to boiling? Well, it's because we all know that there's more water in the bathtub. So what are we really saying? That we have to add more heat to the bathtub full of water because there's just more water present. So what we're saying is that it depends on the mass. The bathtub has a greater mass of water in it than the cup of water. Therefore, it requires more heat to cause this temperature change. What we're saying is that the amount of heat needed to raise the temperature of a sample depends on the amount of sample there is, or the amount of substance present, which is the mass. Now let's take a look at case 2. In case 2, I have 2 cups of water. Let's call them A and B. They have equal masses or equal amounts of water in them, but I want to heat cup A to 50 degrees Celsius, and I want to heat cup B to 90 degrees Celsius. Now I'm going to ask the same question. Which of these would I have to add more heat to get the temperature change I'm looking for? And again, most people would pick cup B, because that answer makes sense. I have to do a greater temperature change, so I should have to add more heat to cup B. So for this case, we could say the amount of heat needed to change the temperature depends on the degree to which, or how much, you want to change the temperature by. So how much the temperature changes by. So we've now related heat to mass and also to the degree of temperature change. That means that heat, which is Q, is somehow related to the mass m and the degree or amount of temperature change, which we can represent as delta T, the change in temperature. And there's actually an equation that relates these together, and that equation looks like this. Q equals m times C times delta T. And some of these terms we've already identified. Q is the amount of heat. That's going to be measured in joules or calories. M is the mass, which we're going to measure in grams. And delta T is the change in temperature, which is typically going to be in degrees Celsius. So that just leaves one term in this equation that looks unfamiliar, and that's this capital C right here. That capital C is specific heat capacity. So specific heat capacity, represented by this capital C, is a constant that's different for each substance that represents the amount of heat needed to raise 1 gram of that substance by 1 degree Celsius. And the units for specific heat capacity could be in joules per gram degree Celsius or in calories per gram degree Celsius. These are compound units, so they only exist the way they do to make this equation work. Here's a table that shows some specific heat capacities for various substances. We have liquid water, solid water, or ice, and water in the gaseous state, vapor. There's also iron shown here. To point out a couple interesting things, the one that absorbs the most amount of heat to cause a temperature change is liquid water. This is about 10 times more than iron, which is interesting because we typically think of metals as substances that are good at absorbing heat. But clearly, liquid water is significantly better at absorbing heat than iron. It's also interesting to point out that water has different specific heat capacities at different phases. Ice cannot absorb as much heat as liquid water, and vapor can absorb even less heat. Let's take a look at how we can use this equation to figure out the amount of heat needed to change the temperature of a substance. This question is asking us how much heat is required to raise the temperature of 250 grams of water, liquid water, by 47 degrees Celsius. So because I have a temperature change by 47 degrees Celsius, I know that I need to use this equation. Q equals m times specific heat times delta T. And like always with an equation, the first thing I want to do is identify my variables. So we can start with the 47 degrees Celsius. We just said that that is the amount of temperature we need to raise it by, so that's the change in temperature. So delta T is 47 degrees Celsius. It also tells us that we need to raise the temperature of 250 grams of water, so that's going to be our mass, 250 grams. And the question is asking how much heat, so heat's going to remain our variable. That leaves this term C, and C is a specific heat capacity of the substance. Remember, C depends on what substance you have. So in this case, we have liquid water. So we would look up the specific heat capacity of water in the table, and we'll see that we can choose between a constant that is in joules or a constant that is in calories. And the one you pick depends on what the question is asking for. Now, I didn't specify it in this example, so I'm going to go with joules. So my C is going to be 4.18 joules per gram degree Celsius. Now that I have all my variables identified, I can go ahead and plug these in. Q remains a variable, and I set it equal to 250 grams times 4.18 joules per gram degree Celsius times 47 degrees Celsius. If I now evaluate this side of the equation, I'll see that Q equals 49,115 joules of energy. This is how much heat is required to raise this much water by 47 degrees Celsius. That wraps up our lesson on specific heat capacity. Write down any questions you have in your notes and bring them with you to class.